So perhaps no, in our electric flux video no, that I've shared with you, no, we've seen no, some of these lines coming out no, of a certain area. No? So there is this flat surface probably, or a curved surface, no, like a sphere. And you have these electric lines of forces that are coming out no, of a given no, area no, or some electric field. No? And again, no, we determine the value of the electric flux no, considering a certain area. No? And to determine the electric flux, no, we realize that we we have this very wide, probably, no, very wide, no, so something like a surface that we call as a Gaussian surface, no, and this is how we relate the value of the electric flux, no. So we relate that to some electric field value last time, no? And we have this one, no. So we can actually no, relate our value of the electric flux. So there's a symbol for our electric flux that appears like this. No? So this is how we determine our electric flux. And that A value is what we consider as a Gaussian surface. No? So it could be any area, no? So like a sphere. No? So how do you find the area of a sphere? No? The surface area of a sphere. No? So the surface area of a sphere, now according to our knowledge in math, is 4 pi r square. No? So if there's a charge inside our sphere, no? So imagine this, no? So if you have a charge inside, no? And it is inside a given sphere, no? So may ara ka sphere, this so the sphere is again no a ball, no? It's like a ball, no? And since it's a ball, it does not have only these lines, no? There's an area, no? If you try to flatten the sphere, no? There's an area that is equivalent to that, no? And again, no? The surface area of a sphere, no? If you consider a sphere, is equivalent, guys, no? So if you have a sphere, no? So its area, surface area, is equivalent to some value like 4 pi, no? And then you have your radius, and we square this radius, no? So that's how we determine our area of our sphere, no? So we square this value r here, no? So r is your radius, no? Of course. So again, no? So the electric field that is coming out of this charge now will eventually fill this area outside. No? So something like they are all over the area. Okay, since the charge is inside the given sphere. No? So this will be our A. No? So the A that you see somewhere here, no, is that surface area of the sphere. No? Now that electric field that is coming from the positive charge inside the sphere will now give you, the electric flux. No? So so this electric flux is denoted by this notation, no? Something like a circle with a line. Others would, I think, no, call that phi symbol, and then there's a subscript E, no, to denote that that's the electric flux. No? So this is one equation that we have. No? And another one that we also no, notice or have no, in that summarized version no, of our video is no, is the concept no, of the electric flux, no, which we can shorten no, by denoting it no, with this symbol. No? So if again, if we will draw the equation, so you can have your electric flux. No? So if you'll denote our electric flux something like this, no, with a subscript E, then it is also equivalent to some symbol, no, which is your charge Q inside. No, so if you have there Q, and we divide Q, no, by this epsilon value, no? So E sub O, no? E sub mute, no? Onto some symbol. So it looks like a letter E symbol again, no? But it is written something like this, no? The like a number 3 with a subscript O, no? And this E sub O, no? I think that's 8.85 10 to negative 12, no? So that's the value of this notation below. So if we want to find, no, the electric flux, we may as well now use this notation. No? So there are two formulas that we can eventually use, no, for electric flux. No? So this one and this symbol. No? So again, no, that those are just our summarized uh, form for our electric flux value. No? So again, considering the concept of what we call the electric potential again, so this is the other thing that we watch in our video. Now, if we are able to hold together all positive charges, we will understand that since they are all of the same sign, their natural tendency is to run away from one another. And I think you will agree with me on that one. They will be exerting repulsive forces with each other. So that's their natural tendency, or that's their potential. Potential to probably explode or to move away, move away from one another. So the arrows here are simply the chance for these positive charges to move further from another positive charge, because that's their natural tendency. Now we realize that in an atom, of course, there are tightly bound protons inside the nucleus. So the nucleus are that's a different setup in the case of an atom. But when we put charges that are of similar nature, our basic law of electrostatics tells us that they will repel one another. So this is their natural tendency to run away from one another. So therefore, now if we consider maybe 2 points here now, so it will start from a region probably with lesser potential, and then it will move towards a region of higher potential. That is if you have a charge that is given to you, or a negative charge that is given to you, or if we consider a negative charge. So a negative charge moves from a region of lower potential to a region of higher potential, given the chance that it will be made to move. So here is our negative charge A. So its natural tendency is to move towards a positive charge. So A could be considered a point of lower potential, and B, a region of higher potential, and that is its natural flow. Okay, so it could never be the other way around. So again, the ability of this charge to move is dependent on the potential of the two given points. Now, the electric potential V, or the voltage, we can denote it with W over Q, or W there represents work. So work over charge is equal to voltage. Or again, we can also relate work with potential energy. So usually the change in the potential energy allows you to do some kind of work. So if a ball is placed at the top of a table and I am going to lift it up, you notice that I change its potential energy. So delta PE, or change in the potential energy, is also causing that object to be, if you will be performing some sort of work there to be able to transfer the object from the top of the table to a higher location. Well, the same way with charges. So when charges are being moved, then you are actually doing some kind of work there. So work over charge, or joules per coulomb, is equivalent to a unit called voltage, or volt. So electric potential, which is denoted in terms of a unit called volt. So we can also write in equivalence work and potential energy. No? So again, the negative charge will always go towards a positive charge. No? So there's a difference there in the electric potential of the 2 points, A and B. Now, when you have varying potentials, so you could have a potential difference between two given points. So again, now we have this potential difference work over Q, which is now your two differing electric potential points. Now V1 and V2, we can get their values by having an equation that is equivalent to I don't know if we have it here. So we have here KQ over R. So our charge, guys, can exhibit a potential equivalent to KQ all over R. We can denote our value V. So V, ladies and gentlemen, so if we will solve for V sub 1, so what's the potential at point 1? So point 1 is of distance R sub 1 from Q. So Q is the charge that is creating the voltage. And then R sub 2, all the way here, there's another point. Maybe these 2 points will have two different electric potential value because they are of different distances. Now they are created by they are caused by first your Q, and Q being at two varying distances. First R1, so that's the value of V sub 1 probably. So if there's a shorter distance, maybe you will have a higher potential for V1. So that's your V sub 1. So V sub 1 and V sub 2 are created due to the distance of charge Q from two different locations. Now our V sub 2, if you want to find V sub 2, so it's still due to Q1 or Q, this letter Q here, but its value is KQ over R sub 2. So probably because it's further, it's much further from Q, then we can expect that our V2 will have a lesser value as well. So this is how we probably determine our V1 and V sub 2. That is with respect to the charge that is creating the electric potential at these two different points. Now our value of K, that is still 9 times 10 to the positive 9. And we encounter this value K when we have our Coulomb's law equation. Okay, there's a question in our chat box. Let me see that. So the unit of our electric potential is in volts. So one volt. So if you our equation last time or previously so if volt also is equal to work over Q, then that's equivalent to 1 joule per coulomb. So that's W over Q. Now that's our electric potential there. Okay, but anyway, this is how we get our V1 and maybe V sub 2. And if you will get the difference of V1 and V2 or V2 minus V sub 1, then that is creating a work already on a given charge. So if you will let this charge move between these two given points, then you have your potential energy that you will need to be able to move those two given points. So again, we have our value delta V. So this one. So if you will have 2 points now, then that will be equivalent to this given equation. So maybe now, in summary, those are the things that we have to remember now, if we have our lesson on electric potential. No? Okay, so again, now moving on, no, and we covered no, in the last video that I asked you to watch is about the capacitor, no, and the capacitance inside the capacitor. No? So basically, this is our electrolytic capacitor. No? This one that looks like a tank. No? So they are so small. No? If you actually see these devices. No? Now in our screen, maybe now we have a large image here. No? But in reality, now these are very, very small images. No? Or small devices. No? Now there are also mica. I think we call this the this flat one. No? The green flat circular disc. No? That's also a capacitor, but that's I think they call it as a mica, no? Mica capacitor. Now, what we encounter basically now with capacitors is that we are dealing with parallel plates. No? So at the very beginning now of the way they understand capacitors is that they come in in these parallel plates. No? Now, these parallel plates are separated by some kind of a distance. No? So if you look at the parallel plates, they are not touching each other. No? So there's a distance between them. No? Distance of separation, I think. No, that's what they call it. You can put air. Air is an insulator. No? So the charges can never jump no, from one location to the other if you put a space in between them. That's the reason why we separate the plates. No? Now, this separation here no, is so obviously wide. No? And kung amo ni kalayo ang aton actual gid nga capacitor, no, we may not be able to create no a very good device no nga capacitor kay you will occupy a lot of space no if you are constructing capacitors in such a way that you will put really no a very significant distance no. Now to lessen this space that you will be providing, others will just simply add no a certain paper, a certain insulator in between the plates. No? And that's what we encounter now when we have this electrolytic na mga capacitor inyo. They are so small. Why? Because instead of the air that you place in between, they put no something like a dielectric. No? The word is a dielectric. No? They put a dielectric in between. No? So in the video that you watched before, no, there's a paper that they place in between the plates. No? So again, no, these plates, if you don't want to separate them with air, then you have to provide it no, with a different kind of separator. No? Mera kada nga ibutang the device. No? And maybe now we can call it as a dielectric because a dielectric is an example of an insulator. No? A specific insulator probably no, that is effective in creating our no, capacitor. No? Now again, no, the capacitor, no, we notice that there's Q here, no, that is probably no developed or charged, no, that is developed whenever we put a voltage in our capacitor. No? Now try to notice this example below. No, there's a battery. No, so this long and short lines is an example of a battery. No, now commonly, no, I think no, this long line should have been positive, no, and this short line, these intervals of long and short lines are actually no an indication of a positive side, and this short line is an indication of a negative side. No, but eventually when we attach a battery to a parallel plate, the plates become charged no with one kind of charge. No, so one plate becomes positively charged, and then the other plate will become negatively charged, and therefore there would be an electric force, no, electric lines of forces that will now travel from negative plate no to the positive plate. No, so in between them you will see that there would now be no some electric field, no, or it will be filled with electric lines of force. No, and the arrows will be no from the negative plate towards the positive plate. No. Okay, so that is because there we place there no some voltage no in our plate. No? So the plate becomes charged eventually. No? So charging, no, Q is a result, no, when you put a voltage in between. No? And then there's a factor there, no, that keeps, no, the constant, no, of proportionality, no, as you add a voltage to the plate. And that's what they call the capacitance value. No? So capacitance times voltage, no, will now give you your charge Q. No? So Joule is some unit, no, of capacitance times a voltage V. No? So the higher the voltage, we realize that there will be higher charge that will also, no, be developed, no, in our capacitor. No? Now our unit of capacitance, no, so that K or constant value, no, which we symbolize with either K or letter C. No? So the capacitance C will have a unit, no, of farad. No? Farad. No? So C. No? Now please do not be confused, no, of letter C here. That is the capacitance, no, and the unit of charge, which is coulomb. No? So if C here is a variable, no, so in this equation we have a variable C, and we have a unit, no, for charge, which is also letter C. No? So this unit C here is coulomb. No? Whereas this variable C here, no, is our, no, capacitance symbol. No? So capacitance is Q over V. No? And Q over V is 1 coulomb over 1 volt, no, which is a unit called farad. No? And again, no, farad is short for Faraday. No? So Michael Faraday, in honor of Michael Faraday, no, they shortened the unit of capacitance to farad. No, now we use very tiny values of the farad unit, no, for capacitance, and commonly, no, either microfarad, no, is the value, nanofarad, or picofarad. No, so we will be dealing with very small quantities, no, of our charge, no, when we go into, no, our discussion of capacitance. No? So basically, no, so what we will be dealing with are parallel plate capacitors. No? And in parallel plate capacitors, there are two, no, flat metals, no, that we actually, no, place side by side. And when we attach a battery towards it, no, or between the plates, no, then these plates becomes charge eventually. No? So the one that is attached to the positive side of the battery becomes positively charged. No? And the one that is attached to the negative end of the battery, no, that plate, no, becomes negatively charged as well. No? So there are how many factors involved? One is area, no, of the plate, no, how wide, no, or how small is the area, affects the amount of charge that you can store. No? And likewise, the distance in between. No? So if we make the distance very, very near, then maybe now we can also improve the charging of the capacitance. No? So other factor will be something that you insert in between. No? Instead of simply putting air, we can also have, no, a material substance, no, that you can insert in between to improve the capacitance of the capacitor. No? And again, we call that material that we insert in between as a dielectric. No? So again, what are these factors that affects the charging? Again, or the value of the capacitance, area of the capacitor plate. No? So when we think of area, it's what? It's a square. No? How big is your square or rectangle? The distance, no, how far you place the plates, no, from one another. And then, no, the kind of dielectric that you place there. No? Is paper effective? No? Is rubber effective? No? So what sort of dielectric is added, no, to the capacitor? No? Now again, no, we cannot build a very, very large capacitor, no, because it will be useless, no, to put that, no, in your computer if you have a very, very big, no, capacitor. No? You may end up with a large capacitance, but if the device is so big as well, it's not practical not to build such large no capacitors. No. Okay, so again, no, our capacitor. No? So parallel plate capacitors. So you have a 20 microfarad capacitance. You charge it with a voltage of 5 volts. No? How much is the charge Q no? On our plate? No? So if you recall, no? Q is capacitance times voltage, or voltage no, is Q over C. No? Or C, no? We can also write C, capacitance, no? To be equivalent, no? So C is equivalent to Q, no? All over the voltage, no? Q over V, no? So coulombs per volt is equivalent to capacitance. Please remember, this is different from our equation in electric potential, no? So this is now talking about the capacitance value, no? Okay, so you multiply that, no, and then you'll get your number of coulombs, no, or your capacitor. Now we have also capacitances that we can attach, no, in different ways, no. One is, no, when we have the capacitances to be attached, no, in parallel, no. So we call this is a parallel connected capacitances. Now the symbol for the capacitance are these two lines, guys, no. These two lines that we draw in parallel, no, to one another because of the symbol that we remember, no, na parallel plates, no. So if you see this one, no, these two parallel lines drawn, no, side by side, this is a representation of a condenser. So they sometimes call this condenser, no, or they call this capacitor, no. So there are two names for our capacitors, no. So capacitors, resistors, no, they are in a circuit. Inductors, no, damo na sila da, no. But again, no, ining capacitor again, no, are devices that are used to charge, no, to the devices that can accept or keep, no, some amounts of charge that are useful in a circuit, no. So other things that are found in our circuit, we have inductors, no, may iban pa na da, no, inductors. We have your resistors, no. And maybe, no, ang resistor and maybe inductor, hopefully, no, we will encounter them in our future discussion. But today, no, let's have this, no. So this is our, we call this as a schematic diagram, schematic symbol, I mean, no. So this is the schematic symbol that we use, no, to represent a capacitor. Now these parallel lines that are equal in length, no. Now, if you see two parallel lines but of different lengths, no. So one long and one short line. Now, this is not a capacitor, no. So again, no, we say earlier, no, that this is as an illustration of a battery, no. So this is the schematic symbol of a battery. So that's a dry cell. Whereas, no, this one, no, is the schematic symbol of a capacitor, no. Are you still with me? Again, now we start with schematic symbol. If we connect the schematic symbols of capacitors to a circuit, then we now have a schematic diagram, no? So schema, no? Schematic diagram, no? So you have a layout, no? So here we see three capacitances, no? So these are capacitors, and they will eventually have voltages, no? Now, if across here, no, on this left side, no, we attach, for example, A, no? So over here, no, for example, we let's just cover this, no? Sorry. So let's put a battery here, no? So how do we attach a battery on this end? Again, now you can have, no, some lines there, and you can have no some long and short lines to denote a battery on this end. No? So this is your long, short lines. The long line again is an indication of the positive side. The short line is an indication of a negative side. No? So if you have some series of long and short lines over here, then we mean that we have here a battery. No? Now we can represent a battery in this way, or we can simply write it with some circular symbol, no? and denote it to be a voltage source. No? So other ways, so we call a battery is a voltage source. No? So again, the positive side is at the top, the negative side is at the bottom. No? Then maybe now you can write that with some voltage V. No? Maybe 12 volts. No? So what we have here now is a 12 volt source, no? Battery source, no? And attached to that, no, are 3 capacitances, no? So we place 3 capacitors, no, after that, no? So how do you know that it is in parallel, no? Now you'll notice that if we will try to detach, no? So just imagine this, no? Try to remove, no? V1, no? For example, we will detach V sub 1, no? So if we are going to remove V sub 1, ladies and gentlemen, we'll notice that the other 2 devices are still connected to the circuit. No? So removing V1, it does not affect that V2 and V3 are still attached to the circuit. So that's what we notice when we have parallel connection. No? It never affects the other parts of the circuit. No? Okay, so again, removing this will never change the circuit. The rest of the devices are still functioning. No? So try to remove V2. No? If you detach V sub 2, V1 and V3 are still connected to the circuit. No? So that shows that our device are attached in parallel. No? Now, what if we remove one and the rest of the circuit will not work anymore? So maybe that's a different connection. No? And maybe we can call the connection now as series connection. No? So in a series connection, when you remove only one, the rest of the circuit will not function anymore. Then that is an indication of a series connection. No? Okay. So again, another name for capacitors, we can call it condensers. We symbolize our capacitor with symbols like this 2, exactly equal in length parallel lines. No? So please denote check the difference of the battery from the capacitor. No? Now, the thing about parallel capacitors is that this is how it behaves. No? The voltages, according to this equation, the voltages of our capacitors and the source are all equal. No? So the voltages here are all equal. No? Just like in our home, we notice that our appliances, they have the same voltages because they are all connected in parallel. No? When you remove one appliance in your house, like an electric fan, it does not affect the rest of the appliances in your house. No? The rest of the appliances will still function despite the fact that you detach your electric fan. No? Because again, the attachments or the connections in your house, they are done in parallel. No? So what you notice there is, first of all, the voltages of all the appliances or the capacitors in this case are all equal. No? Now, the charge that is coming from the source here, from the battery, will now get into the capacitor. No? And eventually, they will become filled. No? They will be filled with charges. No? So from the source, from the battery, one amount of charge will go into capacitor 1, another will go into capacitor 2, and another will go into capacitor number 3. No? So they are all provided by the charge that comes from the battery. No? So the battery here supplies the charge, no? But each capacitor will get its own charge. No? So maybe no, the source charge is called Q, or maybe you can call it Q sub T, no? Or just maybe Q, no? Or Q total. No? So that's coming from the battery. No? Now, as it enters the first capacitor, no? So we will have a split. So the total Q will now split into 3 different directions. And likewise, no, our third charge, or third capacitor will get its own charge Q sub 3. No? So the total value of this split charges, so it's just like a water pipe. No? Kung may tubo kasang tubig, no, there's a source, and then it splits into 3 different directions. The water will simply split into 3 smaller pipes. No? But if you add them up, no, it is still equal to the source charge, no, or the source water. No? So again, no, thinking of something like an analogy, no, for charges, no, that splits into 3 different directions. So our total charge Q sub T, no, or Q total is simply equals to Q sub 1 plus Q sub 2 plus Q sub 3. No? Now, if we will try to have our Q and Q being C times V. No? So our general equation for Q is C times V. No? Now, if Q sub 1 is C1 V1, Q sub 2 is C2 V2, Q sub 3 is C3 V3, no? Then you could have your Q total to be C sub T, V, no? And then you'll have your 3 split values of our okay. So again, if we will now combine, then we will notice that the total capacitance in this case, if we will try to relate Q with CV, that the total capacitance in a series or in a parallel connected capacitances is simply adding each capacitances C1, C2, C3, and you'll have your total capacitance already. So for parallel connection, this is how we get the total capacitance. Now, please take note of these 3 equations that are useful when we deal with capacitances that are in parallel. So if there are more capacitances added here, like you add C sub 4, C sub 5, then we will just simply add it to our equation. So again, the charges in our capacitances are being added together. Whereas the voltage in this case are equal because they are in parallel. Okay, so again, the idea of equal voltages is what we see in our homes, because the appliances that you use in your homes, they are all of the same voltage. Now, if you will try to buy an equipment in your house that is only 110 volts, never attempt to plug it in the outlet, because your outlet in your house is 220 volts. So if you bought that equipment outside of the Philippines, most likely it has a different voltage. So therefore, now if it's not auto volt, that it will not automatically adjust its input voltage, never attempt to plug it in your outlet because the equipment will simply be damaged. So so this is how we reason out that voltages are equal whenever we have parallel connection. Okay, so what's another one? So we have our series connection. Try to distinguish, guys, how series connection is made, and how different are they from the parallel connection. So the one above, this one is parallel connection. This one is a series connected capacitances. So maybe if this is V sub 1 on the left side, V sub 2 on the middle, V sub 3 in the right side, no, maybe you can call them as well as C1, C sub 2, C sub 3. No? Okay. Now we have here an equation about its total capacitance, and maybe we can understand its equation by looking at the relationship of Q, C and B. So what we learned earlier is that Q, we learned earlier that Q is equals to CV, or V, we can write V as Q, over C, so maybe so this relationship here allows us to understand why we end up with these equations, perhaps. So this is dividing the value of Q by C. So joules per farad. Okay, C here is your capacitance. Our unit of capacitance is farad. Now, what are things that we have to remember or to denote whenever we are dealing with capacitors that are attached in series? What are the things that we are to recall? Now, first of all, that our voltages here, so the total voltage V sub T is now equals to V1 plus V sub 2 plus V sub 3. So not like our parallel connection where the voltages are equal to one another. Here, the voltages are dropped, or are dropping, or are split. So the total battery voltage is across the three capacitances. And that total voltage will simply be split apart into three different voltages. Now, what we notice for each charge, however, so as the charge comes out of the battery and enters our capacitors, so the total charge Q, or you can call it Q sub T, Q sub T is the charge coming from the battery. Now this charge that comes from our battery now will enter Q1, and maybe while it is in Q1, you can, or in capacitor 1, then maybe you can call the charge there as Q sub 1. It enters capacitor 1, comes out, and next will enter capacitor 2. Then as it enters capacitor 2, it will simply leave capacitor 2 again and proceed to capacitor number 3. Now what we notice here is that the capacitance, the charges are simply passed on from one point to another without actually changing, because it simply gets in and out of the capacitor. Now once it gets out of capacitor 3, it will simply go back to the battery. And Q sub 3 eventually becomes Q total. So our charge here is never reduced. So next equation that we will notice here is that our total charge Q sub T is simply equivalent to Q1. It's equals to Q sub 2. It's equals to Q sub 3. So the charges are equal in this case, but the voltages are added one to the other. So therefore, if we'll see that V is Q over C, then maybe from our equation here on voltage, the relationship of or finding our value V total will be equivalent to some Q sub T value over C sub T. Q over C is voltage. So that's based on the equation on the voltage. Now that is equivalent to V1. Now V1 is Q1 over C1. And then it says that we are to add the next value. That's Q sub 2. That's Q sub 2, C sub 2. So that's your next value for, and you have your Q sub 3, C sub 3 value. Now again, now this ratios gives you your V1, V2, and V sub 3. No? So dividing them now allows us to go back to our first relationship now of V1 plus V2 plus V3 equals V total. No? Now what we notice, however, is that Q total, Q1, Q2, and Q3 are all equal. No? When they are all equal, then you can simply factor them out. No? And if you can factor them out, no, then you can cancel them eventually. Now, if they are both found on the left and the right side of your equation. No? Therefore, if you factor out the numerator, then what is left in the numerator? Then you could not say that there's zero value in the numerator, but instead, if you factor it out, what is left will be 1. No? So if 1 is left in each of the numerators there, then you'll notice that this equation will now hold true. No? That the total capacitance no, in series connected capacitors are simply the reciprocal no, of each capacitance. No? So 1 over the total capacitance, no, if you add up no, all the capacitance here, then that's just equals to the reciprocal of the first capacitance value plus 1 over C sub 2 plus 1 over C sub 3. And after that, no, you'll get its reciprocal again. No? So that's how we get the value of our no, total capacitance. It's the reciprocal value. No? So please take note of the distinction no, or the difference of our expression no, from our parallel connection. So this is for series connection. No? So proceeding to this example, no? So we have capacitances that are simply no, 1 farad, 2 farad, and 3 farad. No? Now, if we connect them in parallel, so connecting them in parallel, so you see the parallel connection before. No? So if we will answer no, letter A, no? So what's the total capacitance no, if they are in parallel? So that's just C1 plus C sub 2 plus C sub 3, no? Which gives you 1 plus 2 plus 3 no? Farad. So that's a total of 6 farad. No? And I think no, farad is denoted by some small letter F. No? In this case, they write big letter F. So let's have 6F. No? So 6F is your total capacitance. No? So that's for letter A. But what's the total charge? No? If you know the total capacitance, what's the total charge? No? So if you'll solve for the total charge Q, no? So Q sub T is denoted by CT times V total. No? So what's the total capacitance? So the total capacitance is 6 farad. No? While the total voltage is 12 volts. So if you are to find the total charge, no, then maybe it's equals to this one. Ang Monishaton value, yung total charge. No? But I think the question is asking for each capacitor. No? So what do you do no? If it's for each capacitor? No? What will be our answer? No? Now, if you multiply these two, then this one gives you how many coulombs? That's 72. No? That's 72 coulombs of charge no? That you will eventually have. No? So total capacitance and total charge. No? Now, what about for each charge? Now, how about Q1? No? Now, if you'll solve for Q sub 1, then that's C sub 1, V sub 1. No? But what's V? So if the supply voltage is 12 and they are connected in parallel, then each capacitor will receive 12 volts each. No? So the first capacitance is 1 farad no? Times 12 volts because again, no? If it's in parallel, then they will have the same voltage. No? So the first value of the capacitance is 12 farad. No? I don't know, 12 coulombs. No? So that's the first charge no, that you will have. No? Q sub 2 will be C2, V2, and Q3 is C3, V3. No? And eventually, if you add them up, no, they should end up now with a total value of 72. No? Okay, are you following? So Q1, Q2, Q3. No? So you'll just simply use C1, B1, C2, B2, and C3, B3. No? Now, what about if they are in series? No? How do we approach, no, our value? No? So what's the charge in each capacitor, no, if we are dealing with series connection? No? So series connection again. No? So for number 2, for series connection, you have capacitors that are drawn probably like this. No? So you have 3 of them. There are 3 no, lines like this, and you connect them. You connect them no, in series. No? So these are connected in series. Now, one thing we notice if they're connected in series is that the total charge Q is the same all throughout. No? So actually, there's just a need for us, no, maybe not to find. No? So maybe no, again, no, the Q total here is equals to Q1, Q2, Q3. No? That's the relationship in series connection. No? So maybe now all that we need probably is to find Q total. No? And how do we get Q total? It's C total, no, times B total. No? So the total voltage is 12 volts. The only problem is how much is C total. No? And C total is 1 no, over C total if it's in series is equal to no, 1 over C1 no, plus 1 over C2, and lastly no, 1 over C3. No? So, kaunta lang ng reciprocal values nila. No? Okay, so what is the value of our total capacitance? Again, now we could not directly get the value there. No? But 1 over C total is equals to what? No, what's the first capacitance? That's equals to 1 over 1 no? Plus 1/2. No? Are you with me, guys? Kaya ma-reciprocal kita. And then next is 1/3. No? Kay 3 farad ang dason. So we have 1 over 1 plus 1/2 plus 1/3. Can you give me the fraction value for this, guys? What's 1 plus 1/2 plus 1/3? No? Can somebody give me an answer here? No? So 1 over C total is, what is the fraction value? That's 1. What's the answer? What we have no again is 1 over C. C total is 11 over 6. No? Now getting the total capacitance is not yet answering the question. No? So, and however, 11 over 6 is not yet an answer no, of the total capacitance. So how do you get the value of the total capacitance C sub T? No? Now, if 1 over C sub T, now look at this, no? 1 over C sub T. If 1 over C sub T is 11 over 6, then if you'll get the reciprocal of 1 over C sub T, or say C sub T over 1, then what you do is also divide, no? 6 divided by 11, no? And you'll notice that your C sub T actually no, becomes a small value, no? It will become a decimal value, no? Can you give me 2 decimal places for C sub T? So our C sub
0.55, sir.
So we have 0.55 farad, no, for our total capacitance. Now, since the total capacitance now allows us to find the total charge, no, and total charge Q sub T is equal to Q1, no, kay series connection palarehas ang charge, no, is equals to Q1 equals to Q sub 2 equals to Q sub 3, no, and therefore our total capacitance now, or total charge Q sub T, is equals to C sub T VT, no, or 0.55, no, times 12 volts, no, but that's our total voltage, no. So our total charge is how much? Something like 6, no.
6.6, sir.
So we have 6.6 volts, no, so just a little more than half, no, of 12, no. So that's no, not volts, but sorry, no, it's coulomb, okay, it's a charge, no, so it's coulomb, or you can write simply letter C, no. So that's the total charge, and that's the charge in each capacitor, because Q sub total is simply passing, no, from capacitor 1 to capacitor 2 to capacitor 3. So they will have the same charge all throughout, no, until this charge goes back to the battery, no. So if you complete your circuit, there's actually a battery that is attached below, no, to our Q1, Q2, and Q sub 3, no. So again, no, the significance of the total charge, no, to each value of the charge also passing in each capacitor, no. So again, no, your answer for your problems, no, are found in this page, no, or in this slide, the next slide, no, which is consistent with our answer, except that we have, no, a 6.55 coulomb answer here, because maybe, no, this value was not, no, rounded off, no, so they use 6/11 instead of 0.55, no. So 6/11 is the exact, no, or the, yeah, no, the exact answer, no. Okay, so that's our series and parallel connected capacitances or capacitors, no, and that's the example that we just have, no. Now again, now the only thing is we do not actually use, no, an exact 1 farad, no, or 2 farad value, because the size of our capacitor there must be, no, a very big capacitor, no. And in real life, no, there's no capacitor, no, that can hold this much of number of capacitance, no, that is exactly 1 farad, no. So usually they are in micro, nano, or in picofarad value, no.